Welcome to the Chapter 4 Part 2 video. We'll be talking about 4.4, 4.5, and 4.6. Starting with 4.4, our objective is to use triangle congruence in corresponding parts of congruent triangles to prove that parts of two triangles are congruent. So what does that mean? That means we're using the congruence theorems that we just learned to prove that triangles are congruent. And then we're taking that one step further to say if the triangles are congruent, then all of their parts must be congruent. So remember, our original definition was that we had 6 congruent parts, and then we said, well, we really only need 3 in order to prove it. And now we can say as long as we have those 3, then the other 3 must also be congruent. So if we're looking at these two triangles and we know that the triangles are congruent, how do we find the length of OD? Well, since the length of segment OD is not labeled, we can get that length from its congruent triangle. So here we see OD is the second 2 letters there. So then OD has to be congruent to AK, which means we can take the length of segment AK and say that OD equals 6. Okay, and why can we say this? Well, the theorem that we're using, or the postulate rather that we're using, is CPCTC. And what that stands for is corresponding parts of congruent triangles are congruent. Corresponding parts of congruent triangles are congruent. So what does that mean? That means if I have 2 congruent triangles, then that gives me 3 pairs of congruent angles and 3 pairs of congruent sides. So first we need to get congruent triangles. Then, after we have those congruent triangles, we know that their corresponding parts are also congruent. Okay, so what will this look like if we're doing a proof? Here's kind of a skeleton. So the skeleton of the proof is that the first part remains the same. We'll start with whatever we're given. We'll do some steps to get some more congruent statements. We'll be able to prove that the 2 triangles are congruent. And then after we know that they're congruent, we can actually say we also know angle, angle, side. After we know that they're congruent, we'll be able to say that their parts are congruent. So let's review. How do we know which parts match up? Well, from the congruent statement, the first angle matches with the first angle. We say that those angles correspond. So we can say angle E is congruent to angle H. The second angle and the second angle, angle F and angle I are congruent, and then G and J. For the segments, we need 2 points, the endpoints of the segments, so we'll say EF, and that corresponds with the first 2 vertices of our other triangle, HI, and then FG with IJ, and then GE with JH. And notice if I was matching these up, right, EH with EH, FI, FI, so it's almost like substitution, where we can replace each of these vertices with the opposite corresponding vertices. Let's try making a proof. Okay, so here, notice we're given B is the midpoint of AE, AD is parallel to EC, and we want to prove that 2 other segments are congruent. Well, if I don't have any information about those segments, in order to prove that they're congruent, we need to prove that the triangles are congruent, and then use CPCTC. So let's start by marking what we know on our diagram. B is the midpoint of AE, doesn't give us anything to mark immediately. AD is parallel to EC, that we can mark with arrows, not congruence marks, but arrows. And we know that because it is given. And step 2, is to use that information in order to find what congruences do we know. And so we are going to, first I'm going to write my z's. So let's do AE as my first transversal. There's my first z. Those two parallel lines have another line that crosses through it, and that is CD. So I actually have a second z here, which is going to give me two pairs of congruent angles. And so we can say the yellow angles, angle C is congruent to angle D, and also the orange angles, angle A is congruent to angle E, and that is by alternate interior angles. Okay, so we use the parallel lines. What about the midpoint? Well, separately, if I have a midpoint, that means I have two congruent segments. And so if B is the midpoint of AE, that gives me congruent segments on either side of B. And so we can say AB, segment AB is congruent to segment BE, and that is by the definition of midpoint. Okay, so now let's look at what we have. We have two angles and a side. As long as we have one side and two angles, that tells me I can use the congruence theorem, but which one do I use? Well, the side is not the one between the angles, so it's the side outside of the angles. Angle, angle, side. So step 4 is to use angle, angle, side. Now, I'm not proving triangle congruence, so I need to write these two triangles, and I need to make sure that I write the congruent statement with corresponding variables. Okay, so the first triangle, it doesn't matter which order you put them in, but the second triangle has to match the first one. So the way I like to do this is I use my angle congruence marks, and I'll go 0 marks, no marks, 1 mark, 2 marks. And I just go in the order of how many marks there are so that it's easy for me to remember and to match up when I do the second triangle. So I'm going to say 0 congruence marks, 1 and 2. And that way it's easy to match over here which angle corresponds with B, the one with 0 congruence marks, which matches with D is the 1 congruence mark, and which matches with A, that's the 2 congruence marks. Now the other way to think about this, because we have our highlighted colors, you can think of the yellow and orange angle, then the yellow angle, then the orange angle. But think about how each of these variables corresponds within the triangle. Okay? It is very specific the way that you write that congruent statement. So now that we have that the triangles are congruent, after we have the congruence of the triangles, now we can say that means each of the parts is congruent. So since the triangles are congruent, that means that DB is congruent to CB. And we want to write it the same way the proof statement is written. DB is congruent to CB by CPCTC. Let's look at another proof. All right, for proof 2, we are given, and that's what we're going to start with, is the given statements. Segment JL is congruent to segment LM. Also, angle JLK is congruent to angle MLK because it was given. So let's mark it on the diagram. JL, LM, angle JLK, MLK. I have a side and an angle. I need another side or another angle. We have this reflexive angle. So step 2, LK is congruent to LK by reflexive. We'll give that 2 marks. Step 3, now I have side, angle, side. Side, angle, side. So I need to name my triangles for the triangle congruence statement. Okay. Again, the first triangle doesn't have to be specific, but the second one has to match. So if I choose my first one carefully, the second one will be easier. So I'm going to start with my congruent angle, L, and then I'm going to go across my reflexive because that is 2 congruence marks. It's going to be easy to remember to go across the same way. So L, K, J. That was my congruent angle across the double congruent side. So then my second triangle, starting with the marked angle, is L. Across my reflexive side is K, and the last vertex is M. And that should show me that angle J is congruent to angle M. It does indeed. And so our final step is to match our proof statement. Angle J is congruent to angle M by CPCTC. Let's keep going on number 3. If we're given that 2 segments are congruent, these 2 segments are congruent, and this time we have the measurement of an angle. So let's go ahead and start by writing our given statement. AD congruent to CB, AC congruent to DB, and the measure of angle C is 112 degrees. And mark it on our diagram, AD with CB, AC with DB, okay? And the measure of angle C is 112 degrees. I want to find the measure of angle D to be also 112 degrees. Well, in order to find that angle measure, we need congruent triangles. So how do we show that these 2 triangles are congruent? So far we have 2 sides. I need either another side or the angle between those 2 sides. Well, there's no way to prove right now that angle D is 112. That's what we want to prove. We don't have that information yet. So instead, let's see if we can find the third side. We have the reflexive property that tells us, step 2, segment AB is congruent to segment AB. And now we have what we need to prove SSS. So we're going to, again, carefully name these triangles. I'm going to start with ABC. I don't have any congruent angles, so that's going to make it a little bit more difficult to name these sides. So I'm going to say, how do I know which angle corresponds to angle A? Well, angle A on triangle ABC is between the 2 and 3 congruency marks, right? So I'm going to go ahead and put like a little dotted congruency mark there and say that angle has to be between the 2 and 3 congruency marks again. And so that corresponds to vertex B. Okay. Then from A to B, I go along the 3 tick marks. So from B to my next vertex, I'm going to go along the 3 tick marks. BA and our last vertex D. Okay. And so now I have my triangles are congruent. And step 4, somehow I need to use that in order to prove that angle D is 112. Well, I know that angle C was 112. So is there a way to say that C and D are congruent? Indeed they are. I can say angle C is congruent to angle D by CPCTC. And finally, I can now say that the measurement of angle D equals 112 degrees by, we had angle C is 112, right, is in our proof. Now we have their congruent, and therefore this is the transitive property of equality. Okay. If you wanted to put this statement as an equality as well to make it clearer why is that transitive, you could put the measurement of angle C equals the measurement of angle D. That's still by CPCTC. So you could do either one of those statements for this proof. Let's look at the next proof. All right, so for number 4, we have segment AN is perpendicular to segment NL. Mark that on my diagram. EG is perpendicular to NL, EG, NL. Mark it on the diagram. EG bisects NL. Bisecting does not have its own mark, but we do know that it's going to give us congruent segments. And AG is parallel to EL. AG, EL. How do we know all of that? It was given to us. Step 2. Okay, so be careful. This is when there's a lot of temptation to think of those arrows as congruency marks. They are not congruency marks, they are parallel marks, and that's why I like to almost always immediately draw my Z as soon as I have those parallel marks. Okay, so then the question is, which transversal are we going to use, right? Because we have 2 transversals here. We have this vertical line here and the horizontal line here. Okay, so let's look at what happens if I use this line here. Okay, well, that gives me an angle outside of my triangles, right? So my alternate interior angle there is outside of my triangles. It doesn't give me the information that I need within my triangles. And so instead of using that Z, let's see what happens when I use the other transversal here. So I go here, here. Well, I need to go this way, right, to make my Z. And so here, my alternate interior angles are again outside of my triangle. But remember, those are not the only 2 angles. That's not the only angle relationship that we know for parallel lines. Notice here, I have this angle is inside of a triangle. And now, if we think about this is that other parallel line, and therefore we have a corresponding angle inside of the triangle. Okay, so this should look familiar. We did some practice with this last class, but it does take some practice to know how do I know which angles to use when I have parallel lines. And the answer is the ones that have some use. I know it seems kind of like, why did I choose those 2 angles? And it's because they're both inside the 2 triangles that I want to be congruent. Okay, so look at the angles that those give you. It might help also to draw a second diagram with those 2 parallel lines extended. And then you can say, here's E, G, and L. So where are the angles that are going to be useful? Okay, and that might make it a little bit easier to see that those are 2 corresponding angles. So we have now angle AGN congruent to angle ELG by corresponding angles. We also have this statement about bisecting that we haven't used. And so step 3, we can use EG bisects NL, means cuts NL in half. And so we have NG is congruent to GL by definition of segment bisector. Okay, so we have an angle, we have a side, and we have these right angles marked, but we haven't said that they're congruent yet, so that should be our next step. Step 4, angle ANG is congruent to angle EGL. And why can we say that? Because all right angles are congruent. Okay, so now we have angle, side, angle, and the side is between the 2 angles. So we have 2 angles and the side between. That's ASA, not AAS. AAS is when the side is not between the angles. And so we create our triangle congruence statement very carefully. Again, I'm going to say congruent right blank. So GNA, congruent right blank. LGE. Okay, and I'm just realizing we are not using CPCTC this time, so I could have just taken the name from the proof statement. I'm going to go ahead and cross this off and say, actually, I need this to match my proof statement. Triangle ANG congruent to triangle EGL. Okay, we didn't use CPCTC for this one because we weren't proving parts that are congruent. This time it was just asking for the triangles to be congruent. Okay, that's it for the proofs for this section. Let's look at our next page of notes. So for 4.5, we're looking at special types of triangles. And our objective is to use and apply the properties of these special triangles, which are called isosceles and equilateral. Okay, now we've mentioned equilateral triangles before. Equa meaning the same, lateral meaning sides, the same sides. Okay, isosceles, and I can kind of remember it because it's got this little SOSELE, means that two of the sides are the same, but the other one could be different. Okay, so the first way that we classify triangles is by their angles, triangles, right? 3 angles. So if we have an acute triangle, remember it's so cute, it's small. Acute triangles have 3 acute angles. All of their angles are acute. And then we have a right triangle, which we've talked about before. A right triangle means it has a right angle. You can only have one right angle in a triangle. If I had 2 right angles, the third side would never connect. Okay, we have an obtuse triangle, which, as the name implies, it has an obtuse angle, a larger than 90-degree angle, but you can only fit one of those in a triangle. The other 2 angles will always be acute. And then finally, we have an equiangular triangle. Equiangular, all of the angles have the same measurement, which we said in a previous video will be 60 degrees for all angles. Very specifically, it will always be 60 degrees, which means that this is a very special case of an acute triangle, and all 3 angles are congruent. Our second way of classifying triangles is by their side length. And so our first way is if I have scalene triangles, that means that all 3 sides are the different lengths. So we have 0 congruent sides. All 3 sides are different lengths. Our second type of triangle is if we have 2 sides that are the same length. That's that SOSELE reminder, right? 2 congruent sides. Now, if it has 3 congruent sides, it can still be called isosceles. And so an equilateral triangle is a special case of isosceles triangles where we have 3 congruent sides. And I kind of mentioned before, a little bit of a spoiler, that equilateral triangles will always be equiangular and vice versa. Equiangular triangles will also always be equilateral. And so we can practice classifying these triangles. Classify triangles by the angles and the sides. Always the angles and then the sides. That's just common notation. We're always going to name the angles first. So first, let's look at these angles. We have a 121-degree angle, which is obtuse. As long as there's one obtuse angle, we call it an obtuse triangle. And then we have these little congruence marks that tells me that this is an isosceles. SOSCELES. Our next triangle, we have 20, 75, 85. All of those are less than 90, so this is acute. And then our congruence marks show us that 1, 2, 3, none of the sides are the same. So this is scalene. The next one has that nice box angle that tells me it's a right triangle. The side lengths 5, 12, and 13. None of those are the same, so this is scalene. On number 4, again, we have that little right angle there, so that tells me this is a right triangle. The 2 congruence marks tell me that this is isosceles. SOSCELES. Number 5, All three angles are the same, so this is equiangular. And then the three sides are also the same, so this is also equilateral. Number 6, 11 and 45 are less than 90, but 124 is not, and so this is obtuse. And then we have 1, 2, and 3, meaning none of the sides are the same, so it is scalene. Okay. When we're talking about an isosceles triangle, we have the two sides that are the same and the one side that is different. And so we have some special vocabulary that we use in order to talk about the sides and the angles. And so I'm going to draw an isosceles triangle here. Those are my two congruent sides. And the two congruent sides are called the legs. Okay, so this is a leg and this is a leg. The third side is called the base. So when we're talking about the base of a triangle, for an isosceles triangle, there's only one side that should be called the base. The two congruent legs form the vertex angle. So this one here is called the vertex. The other two angles are called the base angles. They're the angles that are on the base. These two angles are the base angles. So the side and the angles are called base side and base angles. Okay, let's look a little bit closer at isosceles triangles. We have a nice theorem for isosceles triangles that says that the two sides that are congruent are opposite congruent angles. So what does that mean? That means this side is across from this angle, right? It doesn't touch this angle. So if this side and this side are congruent, then the angles that are across from them are also congruent. Which also means that if I have two congruent angles, the sides across from those are also congruent. So I'm going to do this in a different color just so you can see. If the sides are congruent, that means the angles are congruent. If the angles are congruent, that means that the sides are congruent. So how do we write these congruency statements? Side AB congruent to side AC means that the angle that's not in that side is congruent to the angle that is not in that side. If the angles are congruent, then the sides not containing that angle are congruent. Okay, so angle C congruent to angle B. The segment without C is congruent to the segment without B. Let's practice. We want to find the missing value. If segment UM is congruent to GM, this isn't a proof, just practice, so we can just mark it on the diagram. UM, GM, the measure of angle G is 63 degrees. We want to find the measure of M and U. Measure of angle M, measure of angle U. Well, we just said the isosceles triangle theorem means that the angles across from the congruent sides are congruent. So here's a congruent side and a congruent angle. Congruent side points to this congruent angle. So angle U is 63 degrees. So now we need angle M. Well, if we have two angles in a triangle, we can always find the third by the triangle sum theorem. So 180 minus 63 minus 63 equals the measure of angle M. 180 minus 63 minus 63 gives us 54 degrees as the measure of angle M. For number 2, we have our congruences marked here. If I have two congruent angles, that means the sides opposite them are also congruent. And therefore, we have these two statements should be congruent. 5x plus 10 equals 8x minus 8. Solving for x, subtract 5x from both sides, plus 8 to both sides, 18 equals 3x. Divide by 3, 6 equals x. Solve for x and explain. So this was the isosceles triangle theorem to find that x equals 6. On number 1, we should also write an explanation. This was isosceles, isosceles triangle theorem and triangle sum theorem. We had to use both. Okay. Number 3, we have a lot of triangles going on, and so what I like to do is, again with the highlighters, I'm going to highlight segment FD. Segment FD, and I'm going to use a lighter color for this just because I know I'm going to need to highlight over part of this with another color. So I chose a lighter color. FD, and what's the triangle that that's a part of? Well, that's this big triangle here. And so if I redraw that triangle, and I'll go over it in pen as well, we have F, D, H, and we have these congruence marks on angle D and H, which means segment FD is congruent to segment FH. And then we have segment ED, which makes this little triangle here, and that is EDG. And I have congruence marks here on D and G, which means across from those is ED congruent to EG. And that is by the isosceles triangle theorem. Okay, and again, redrawing the picture is just a really good way to make sure that you're using the correct segments for the congruences. All right, 4.6, this is our last section for this video. Our objective is to prove that right triangles are congruent by using the hypotenuse leg theorem. So this is a new theorem. It goes along with SAS and SSS and ASA and AAS. Okay, so this is a triangle congruence theorem. I'm going to put here similar use to SSS, SAS, ASAAAS, because we're going to use them in the same place in a proof, right? We're using them as the reason behind saying two triangles are congruent. So first we need to understand that triangle ABC is a right triangle. This can only be used when there is a right angle, if there's a 90-degree angle. If there's not a 90-degree angle, we cannot use this theorem at all. And the measurement of angle B here is our 90-degree angle that we need. And therefore, AB and CB are called legs. Well, each one is a leg. Together they are legs. And AC is called the hypotenuse. This should sound familiar from the Pythagorean theorem. Remember when we had a squared plus b squared equals c squared, c is always the hypotenuse. Okay, the longest side, the one that's across from our right angle. Think about our right angle kind of points to the hypotenuse. Just like in the isosceles triangles, the congruent angles point to the congruent legs. Okay, so let's see if we can define this theorem on the next page. The hypotenuse leg, or HL theorem, is if the hypotenuse and one leg of the triangle are congruent to the hypotenuse and a leg of another triangle, then the triangles are congruent. So again, it needs a hypotenuse for this to work, which means it needs to be a right angle. And so we have triangle RSQ with right angles, congruent hypotenuse, and a congruent leg. And so we say which angle corresponds with R is the other right angle, so that's going to be triangle Y. S is between the hypotenuse and the congruent leg, so that's Z. And then the one that's left over is X. So let's determine if these triangles are congruent, how we know, and see if we can write our congruent statement. So here we have right triangles. We have a congruent hypotenuse. We need a congruent leg. Reflexive property says that the legs are congruent. And so to name this by hypotenuse leg, we can say angle PRS. P is the one in between the two congruent segments. So R is the piece between the two congruent segments. R in this triangle is my right angle. So in this triangle, it is angle P. S is left over. Q is left over. On number 2, we have a right angle. We have congruent legs. We need congruent hypotenuse if we want to use hypotenuse leg. We have that C is the midpoint of AD. That will give us our congruent hypotenuse. And so we have hypotenuse leg. It satisfies. I need the hypotenuse. If I have 2 legs and a right angle, that will be side angle side. So not all right triangles use hypotenuse leg. So let's see if we can name these triangles. A is the one between 1 and 2. Between 1 and 2 is D. B is the right angle, that's E. C is the leftover. Okay, what do I mean by between 1 and 2? I mean the angle that's between the 2 segments with 1 and 2 congruence marks. Number 3, I have a right angle. Hypotenuse is 10. This hypotenuse is also 10. Remember, the hypotenuse is the one across from the right angle. The leg, I have 2 legs, both with a length of 6, so that satisfies hypotenuse leg. Right angle, so there really are still 3 requirements. We have the right angle, the hypotenuse, and the leg. Okay, so A, B, C. A is between 10 and I don't know. So between 10 and I don't know is D. B is my right angle. Right angle is E. C between 10 and 6. Between 10 and 6 is F. Number 4, I have a right angle. I need a right angle in the other triangle if this is going to use hypotenuse leg, but these angles are vertical, and so I know that this must be congruent and therefore must also be a right angle. So we have our right angle, the hypotenuse with 2 marks, hypotenuse with 2 marks, leg with 1 mark, leg with 1 mark. HL. I have all the requirements, so let's see if we can name this. MNO. So we're looking at, this is our already named triangle. Angle M is the right angle. So in this triangle, our right angle also M. N, between 2 and I don't know. Over here, 2, I don't know, is P. O, between 1 and 2. L, between 1 and 2. Okay, so that's a couple practices. Let's see if we can apply HL to find some variables. So in example 1 here, we want to find the values of X and Y if the triangles are congruent by HL. We know that the triangles are congruent by HL. So we have our right angle, always good to check. Which one is our hypotenuse? 3y and x plus 3. By HL, I know that 3y has to equal x plus 3. The hypotenuse must be congruent to the other triangle's hypotenuse. Our legs also have to be congruent. X equals y plus 1. So if both of my equations have two variables, how do I solve this? Well, if you remember from algebra, we can use what's called systems of equations. And that means we're just going to substitute for one of the variables. So if x equals y plus 1, we're going to substitute y plus 1 in for x into our other equation. So we have 3y equals x plus 3, but instead of x, I'm going to put y plus 1. And now we have an equation with just one variable. So collecting like terms, 3y equals y plus 4 minus y. 2y equals 4, divide by 2, y equals 2. And then we substitute that back in to find x. X equals 2 plus 1, which is 3. X equals 3, y equals 2. Okay. In our second example, again, we're using hypotenuse leg. These are both right triangles. So here's my hypotenuse and my hypotenuse. Those must be equal. 3y plus x equals y plus 5. The legs also must be equal. Y minus x equals x plus 5. And again, we're going to use systems of equations. If you remember systems of equations, you can use any of those methods. I'm going to continue using substitution because if you're not as comfortable with systems of equations, I find that that's the one that's the least confusing. And so I'm looking at this. This has a lot of coefficients, and so I'm going to solve here for y. Plus x, y equals 2x plus 5. That's what I'll be substituting. So everywhere that there's a y, I'll substitute a 2x plus 5. It might be easier if we simplify this statement first. So let's go ahead and subtract y from both sides. 2y plus x equals 5. Now there's only one y that I have to substitute into. If you don't simplify first, you will still get the same answer. 2 times 2x plus 5 is replacing my y, plus x equals 5. Distributive property. So I get that 4x plus 10 plus x equals 5. Collect like terms. 5x plus 10 equals 5. Subtract 10 from both sides. 5x equals negative 5. Divide by 5. X equals negative 1. Now that I have x, I can substitute that back in to find y. Y equals 2 times negative 1 plus 5. Y equals 2 times negative 1 is negative 2 plus 5. So y equals 3. Okay, that one does require a little bit more of an understanding from algebra in order to solve it now in geometry as well. So if you want more review on that, I'd be happy to go through systems of equations with you in more detail during office hours. Okay, a very last problem for this video is a proof. And so on the next page, let's take a look at it. We need a statements and reasons column to make our 2-column proof. We know that BE bisects AD. That means AD is the one that's cut in half. AB is perpendicular to BC. That gives us a right angle here. DE perpendicular to EC gives us the second right angle here. AB congruent to DE. That gives us those congruence marks. So my diagram is already marked. I'm going to go ahead and rewrite all of the given into the statements. And I'm just copying it exactly. BE bisects AD at C. AB perpendicular to BC. DE perpendicular to EC. AB congruent to DE. Because it was given. So our next statement should be that bisecting Remember, we can't mark our diagram. We have to define it first. So by the definition of it bisected a segment bisector cuts AD in half at C. So now we have AC and CD are congruent. Okay, so what do we have now? We have two sides and an angle, but specifically we have a right angle, a hypotenuse, and a leg. So that tells me we can use HL. If this was not a right angle, it would be SSA, which is not a congruence theorem. So on number 3, using HL, we can name our triangles, name them how they were given, ABC, congruent to triangle DEC. All right, so I'm just going to write underneath this box, our 5 congruence theorems are now congruence postulates / theorems. SSS, all the sides, SAS, ASA, AAS, and HL.